Okay, let's start. So today we will talk about the Boolean algebra. So I hope that you tried Vivado tutorial. You actually install the Vivado on your own machine. And after you install the Vivado, you can import the VHDL file I provided on Canvas and build a project like this. So the VHDL example I provided on Canvas is very simple. It's just a AND gate. So you can load that into this project, and then you can see this is a AND gate. After you have that gate, you can create a simulation like this. And then you can create a waveform. You can set the input of X and Y, and then click the simulate button, and then do the simulation. So this is the output. After is the output. So in this way, you can write a gate and then test your gate. This is the hardware language. So in C or C++, it's a kind of a debugging. You set some signals to your gate, and then you can see the output. So if something is wrong, then you can modify your code. So if you are not familiar with VHDL, here is a tutorial for you. But we only, write some very simple VHDL. But if you are interested in more details or more advanced feature of VHDL language, you can see this tutorial. So in this lecture, we will talk about the Boolean algebra. The basic element of Boolean algebra, or the basic variable of a Boolean algebra, can only be 1 and 0, so all true or false. So Boolean algebra is the mathematical system for the manipulation of variables, which can be 1 or 0. So in the real circuit, we use some switch to represent one variable. Yes, if the switch is on, then it's a 0. If it's on, then it's a 1. If it's off, then it's a 0. So the Boolean expressions are created by performing some operation of Boolean variables like the and, or not. So here are some truth tables for the example gates. Like this is the 2 input AND gate, and this is a 1 input. This is a 2 input OR gate. Because there are only 2 inputs here, then in the truth table, we have a 2 to 2 rows, which is a 4 rows here. It just lists all the possible for these 2 variables. One single variable can either be 1 or 0. So there are totally 4 combinations. And then we can write the output here. For the OR gate, only when 2 inputs are 0s, output is 0. For the AND gate, only when 2 inputs are all 1s, then the output is 1. So sometimes we have a 1 input gate, like NOT gate. So here is a NOT X. So for a Boolean function, at least we have one variable. At least we have one operator, and or not. So at least one input from the set 1, 0. So it can generate an output, which is also a member of the set of 0 and 1. And we know that it's very easy to implement a binary number system by the circuit. Then sometimes we have a more complex Boolean expression like this one. So for this expression, we have 3 variables, x, y, and z. In order to analyze this truth table, we can but if we want to analyze this expression, we can write a truth table like this. Because we have 3 variables, input variables, then we have 2 to 3, which is 8 rows. So in order to simplify the analysis, we can set some intermediate variables like x and z bar. So we can first write the value of z bar like this. It's easy. You just apply the NOT gate on this input. And then you can compute the x and z bar. You can use the value of this column and this column, and then do an AND operation. So when you have the value of these intermediate variables, you can easily compute the last final output, in the last column here. So sometimes you need to set some intermediate variables to simplify the analysis. Again, when we do the analysis, we have some priority on the order. For example, if we have this logic expression, the NOT gate, the one input NOT gate always have the highest priority. So we will compute this z bar first. And then we will compute this AND operation. The AND operation has a second level priority. And then the last one is the OR operation. So when we do the analysis, we have some priority order here. When we know the priority order, we can, based on the order, we can set the intermediate variables like the z bar, because the NOT operation has the highest priority. So we set z bar as the first intermediate variables. And then the AND operation has the second priority. So we set x and z bar as the second intermediate variables. So the current computer system used some digital circuit to implement these Boolean functions. So the simpler we can make a Boolean function, the less hardware overhead we will pay to build that equivalent circuit. And if we pay less hardware overhead, which means that we use less gates, less NOT gates, AND gates, or all gates, we will consume less power. Potentially, your circuit can run at a higher frequency. So this is why simplification is a very important job for the Boolean algorithm. So this is also why we want to reduce the Boolean function to its simplest form. So there are a number of laws and identities that can help us to do this. So here's some laws. For example, inverse law, x and x bar is always 0. X, all x bar is always 1. So no matter the value of the variable of x, how can we prove this? How can we prove this law? It's very easy. You can just write a truth table. Because this is only one variable, so you can write a truth table with 2 rows. And then you can write the value of x and the value of x bar, and then see what's the output for these 2 expressions. So all the laws here can be proved by the truth table. And we also have these laws. You can also prove them by the truth table. For example, here is one example. Because we have x, y, z, 3 variables, then the truth table should have 8 rows, 2, 2, 3. We just write all the possibilities for x and y, x, y, and z here. And then we set 2 intermediate variables. The first one is x and y. Why? Because the AND operation has higher priority than the OR operation. So we group x and y as the first intermediate variable. And the second intermediate variable is x and z. Because we have a 2D symbol here, so this part has higher priority. Then we just write y, all of these here. This is the third intermediate variables. And based on the values in the first 3 columns, we can write the value of the intermediate variables and then calculate the final output of the left part and the right part. And then we can see that the last 2 columns are exactly the same. So in this way, we can prove this law. And we also have these laws, more complex law. I believe the most important law is the De Morgan law. By the De Morgan law, you can simplify x, y, and then a large bar here. In the future, we will frequently use this De Morgan law. When we have these laws, we can do the simplification. For example, here is a equation, logic equation of Boolean expression here. And then we want to simplify this one. Because if we directly implement this, we need a OR gate, NOT gate, OR gate, NOT gate, AND gate, and then NOT gate, one AND gate, another AND gate. So we will need a lot of gates, and then we can apply the laws one by one, appropriate the law one by one, and then eventually we can simplify the equation into this form. So in order to implement this function, we just need one single AND gate. So compared to the original equation here, we significantly reduce the hardware overhead or the gates number to implement the same circuit. So sometimes it's cheaper to build a circuit using the complement of a function than to directly implement it. So in this case, we will use the De Morgan law. For example, if we want to implement this one, we need one NOT gate, the other NOT gate, and then a AND gate. So basically, we will use 3 gates. But if we implement this part, you just need an OR gate and then an NOT gate. So only 2 gates. So in this case, the De Morgan law is very important because De Morgan law can help us to reduce the hardware overhead. And the De Morgan law can also be applied on any number of variables. In previous slides, we just talking about the 2 variables. Now we have 3. So instead of implementing F, we can implement F bar. And then we can apply the De Morgan law on this expression. And then eventually we can get this equation. Again, there are multiple ways to simplify the same Boolean expression. And you may have different results, but these results are logically equivalent. Why? Because they have the same truth table. If you draw a truth table for all the results, then they should be the same. So in order to reduce the confusion, so we will use the so-called canonical form to do the simplification. Because when there are multiple ways to do the same thing, it's very difficult to make the computer or the algorithm to understand how to do that. Then we just create the so-called canonical form to do that. There are 2 types of a canonical form. The first one is the so-called sum of the products. The second one is called a product of the sum. So in the sum of the product form, ANDed variables are ordered together. What does that mean? So we first do the AND operation first, and then we all these 3 items together. So in the product of the sum, all the variables are ANDed together. So we first do the OR operation and then AND these terms together. So let me give you a more concrete example. So again, the old Boolean expression. Then we just draw 2 tables for this expression. By this truth table, I will ask you to write the sum of the product and the product of the sum. Both are the canonical form. How can you do that? So in order to write the sum of the product of this Boolean expression, you just need to pick up all the rows whose output is 1. So we have 4 rows here. 1, 2, 3, 4, 5. We have 5 rows here, which can generate a 1 output. And then we just write each row like this. because this x is a 0, this 1 or this y is 1, and this z is 0. So the first item here is x bar, y, and z bar. So all the zeros here will generate a bar, the inversion of the parameter. For example, the x here is a bar, so we write x bar. So if you have a 1 here in the truth table in this row, then we just directly write that word. Because y is 1 here, we just directly write 1. And the z is a 0, so we write the z bar. So each item here indicates one row. And then we just write all the rows which can generate 1. We have 5 rows here. Then we have 5 terms here. And this one is corresponding to this, the last row. Why? Because for the last row, all values here are 1s. Then we just write x, y, z. So no bar at all. So in this way, you can write the so-called sum of the products, which is one type of canonical form. So for the product of the sum, you just pick up the rows which can generate a 0, and write each row into a odd form, and then add them together. So, but here we just focus on the sum of the products. So we can implement each Boolean function into a circuit. This is what we actually did in the system, in the computer system. A gate is an electrical device that can produce a result based on multiple number of inputs of one single input. In fact, the gate consists of 1 to 6 transistors. But in this lecture, we just consider them as one single unit. One gate is just 1 unit. And one circuit may contain multiple gates in order to implement some function, or in order to implement some purpose. So the simplest 3 types of gates is AND, OR, and NOT. The first 2 are 2 inputs. The last one is 1 input. And we have the truth table here. So actually, this gate contains multiple transistors, but here we just consider it as a unit. So here are some more complex and more powerful gate, which is the XOR gate. The XOR gate means the 2 input XOR gate. The XOR gate is when 2 inputs are different, it generates a 1. When 2 inputs are the same, it generates a 0. So the same is 0, the same is 0. When they are different, you have a 1 here. This is XOR operation. And then we have a NAND operation and a NOR operation. They are also very important. So unlike the AND operation, the NAND operation just add a NOR gate to the output of AND operation. So you can see that except the last row, whose input is 1 and 1, all the other rows are generated 1. the NOR operation also add a NOT gate to the output of OR gate. Due to the De Morgan law, you have multiple methods to implement the NOR gate and the AND gate. The NAND gate and the OR gate, NOR gates, are so-called universal gates because they are cheaper. They can represent all the logic. So basically, in the real chip, we may only have a NAND gate. We only have one type of a NAND gate because it's easier for the designer to fabricate this type of gate. It's cheaper. By this single NAND gate, we can implement an OR gate. We can implement a NOT gate. How can we do that? We just connect two inputs to one input signal, which is X, then the output is a NOT. So this is a truth table of the NAND gate. If we connect Y to X2, then we should have the same. These two inputs should be the same. So we will never have this case, these two cases. We will always have the first row and the last row. And then you can see that this is exactly NOT gate. Why? Because if the input is 0, then we have 1 as output. If the input is 1, then the output is 0. So the AND gate is just a NAND gate plus a NOT gate. This is how you can implement an OR gate. So by the same type of a NAND gate, you can implement all the logic here. That's the reason why it's a so-called universal gate. Sometimes we need multiple inputs gate. And you can always break these gates into the multiple 2-input logic gates. So here is one example. So here is a 3 inputs, X, Y, Z. But we can always use the so-called 2-input logic gate to implement this one. We just need more gates. So when we have a logic Boolean expression, we can implement this expression by one circuit. And this circuit is a so-called combinational logic. Why? Because there's no clock. When you apply the XY signal on the circuit, you can immediately get the output at the output end of that piece of circuit. So you don't have to wait. But in the real case, we will have a clock. We will change the input in every clock, and then you can generate a different output. So here is one simple example. This example shows a half adder. The so-called half adder is that we only have a carry out. We have no carry in. We only have 2 inputs, which is X and Y. The function of this half adder is we add these 2 variables together. The output we have 2 outputs. One is the sum, the other one is the carry. So 0 plus 0 gives us a 0. 1 plus 0. 0 plus 1 gives us 1. 1 plus 0 gives us 1. And we have 2 ones. The sum is a 0. We have a carry here. Then we can implement separately. We can implement sum and carry separately. We just use the XOR gate to implement the sum and the AND gate to implement the carry. But they share the same input. Now, if we consider the carry in, we will have one more input, which is the carry in. So now we have 3 variables. So we have 8 rows here. And then we can add these 3 together to get the output here. So this is so-called full adder. And the full adder is the adder we used in a multiple bit adder because we can have both the carry in and carry out. And then we will use a more complex circuit to implement this one. And you can try it yourself. Any question? Yes. For this case, it's not just a XOR gate. It has multiple gates here. You can do the simplification yourself. How to do that? You can use the canonical form. You can pick up, the ones, the row has ones here, and write them into the canonical form and do the simplification. Because you have 3 inputs here, you cannot just use a XOR gate to implement it. Maybe 3 input XOR gate. Any other question? So if no question, we can stop today. Thank you very much. If you haven't installed Vivado, please do that.
For that homework, right? So we have to implement, I think, 5 gates.
Yes.
Yeah, those are all, I think, already within the HDL primitives, right?
Yes.
So when we do that, those, at least from the example that you showed, should those all be their own Vivado projects? And then we like.
It doesn't matter.
It doesn't matter.
It doesn't. I just want everybody to try the IDE, the Vivado, try to get familiar with the environment. Try to write some simulation waveform.
Okay, yeah. And how comprehensive should our tests be for those? Should we be testing, both bits, every possible, logical operation in the Boolean and truth table?
Yes, you can do that. At least you can test one possibility, right?
Oh yeah, one possibility. I'm just wondering if
you don't have to list them all, but I think 1 or 2 is good.
Yeah.
You don't have to test all the cases.
Okay.
Thank you very much.